Okay, so welcome everybody to the seminar today. So today we are very happy to have Professor Roberto Pignatelli from Trento University of Italy, and he's going to talk about the simple 1-2 vibrations. Yes, so thank you. So please start.
Thank you very much, Yonkai. And first of all, let me thank you for the invitation, and all of you to be here to follow my talk. I'm going to present a research, and I'm very is the thing I'm. Let me open. Where is my slide? Oh gosh, I lost just a moment. Okay, let me share the slide first, and then speak. Here, okay. So just the time to find a way to. Not I can do it full screen. I could do it before. Yeah. Okay, sorry for the little problem. So this is well, something I worked hard in the last years since, and it's very nice for me to present here in Taipei, although online, because as you know, for sure, in the audience, there are people that know much more than me on this subject, and so it's for me very nice to be able to present it, my little contribution here, and of course, comments are very, very, very welcome. Any comments or on this work. So this is a joint work with Stephen Coughlin mostly, and for the last part, I will say I'm going to say something about well. But you see, one of the main results is with Yong Hu and Tong Sang, which, well, I'm going to explain how we met online, of course, and our research met, and we got something I think interesting in common. And so the subject is vibrations 1-2 surfaces, which I'm going to say quickly what they are. And well, let me go to the overview of the talk. So first of all, I'm going to the first, as usual for my talk, the first part of the talk is going to tell you something you know very well, I think, everybody, but it's always good to recall it at the beginning of the talk, things, you know, that everybody very well known, but we make in common, we at least you see how I think about these things, and we make sure we have a common language. Then I'm going to discuss a bit about vibrations. So not only vibrations in 1-2 surfaces, which are the subject of the main subject maybe of the talk, but a little bit about the inspiration of the work, the main idea that is behind the work, which comes from the theory of surfaces and the genus 2 vibrations. Then the biggest, I think, section is about trifles on the neutral line, which is the main application we have of this vibration strategy, and the study of the moduli spaces, which is the goal and that we had from the very beginning, as I will explain. And the last section is about some future work. I mean, we are doing now, we're trying to work now about the geography of the trifles of general type. Well, a little bit I understand about the geography of trifles of general type and the game of the Gorenstein index of the trifles seems to play a little bit in this game. So again, please interrupt me when you want. Any question a comment is welcome. Let's start with calling you what is volume and genus. Maybe I should make it smaller so that you can see the slide. So what are volume and genus? So the subject of the talk will be X will be, during this talk, always a complex projective variety. And I'm going, well, to assume always that the singularities of X are at most canonical. The reason for the canonical singularities of X is that I want to study moduli of threefold general type, and so moduli of varieties of general type. And if I want to study moduli of varieties of general type, I have to study the canonical models. And the canonical models of varieties of general type are not smooth, but the singularities are at worst canonical. So that seems to me, or at least the whole work we did is on this assumption. Smooth is too strong. And allowing singularities that are not canonical doesn't seem really useful at all. So the genus is, as usual, defined as the H0 of Kx, the dimension of the spatial global section of the sheaf associated to the canonical divisor, to a canonical divisor. For the volume, well, I like this definition, which is total, I think. Well, I don't know who did it first, but this definition of volume is for a variety is this lim sup. You take the sequence of H0s, not more of Kx, but of the multiples of Kx, and this is grows for m going to infinite as a polynomial whose degree is at most the dimension of the variety. So n is the dimension of the variety. And if this number, so if this ratio, so divided by m to the n, so this makes 0 if the polynomial is smaller degree, otherwise it's positive. And then with a little correction, by n factorial defines the volume. So that, in fact, this is a good definition of variety of general type. The varieties of general type if this number is positive. Variety of special type, and as you know, several classes are very interesting. Those have volume 0, but this talk is about varieties of general type. And the varieties I'm mostly interested in are the canonical model. Now we know that for every variety of general type, there is a unique canonical model, which is the proj of the canonical ring. And these have canonical singularities at worst canonical and ample canonical divisor, which is then the assumption, the objects I'm mostly interested in, although I'm going to allow something more here. So, however, it's important to know that genus and volume, so defined, is a birational invariant, since, well, for a canonical model, the volume is the self-intersection of the canonical divisor. And so in the future slides, whenever I will have a canonical model, I will probably use k to the n, which I'm more used to as a definition. But I think that's a good definition is this one, because it's a birational invariant. We are doing birational geometry in some way. Some introduction, again, very well known to everybody, I think, is following. What happens in dimension 1 is obvious part of any course, say undergraduate course in algebraic geometry, that the curve, the volume is 2G minus 2. I wrote it as PG. For curves, the genus is usually denoted by G. So it's an even number, and the minimal genus general type is 2, and the volume is 2, otherwise 2G minus 2. If we move to for surfaces, it was known already to Max Netter that there is no more. So dimension 1 is the two invariants are essentially equivalent. There is a linear relation among them. In dimension 2, this is no more true, and there are two, in fact, inequality. The simplest one, the oldest one, is the neutral inequality, which can be written in this way: the volume of a surface is an integral, and that is at least 2pg minus 4. Well, there is another inequality, which is known as Bogomolov-Miewo-Kayao, which says that the volume is smaller than 9pg plus 9, but it's more difficult, and it's far from the scope of this talk. So this talk is about the neutral inequality, and the neutral inequality for threefold, which has nothing to do with Max Netter now, but is, of course, named generator by analogy in dimension 2 is due to Yunkai, which is in the room, Meng Chen and Zhang Chen. And I think this is the best version I know, which is this paper on Diocon 2020, which says that the volume is at least, the inequality is 4/3 PG minus 10/3, and at least if you assume PG smaller than 4 and PG bigger than 11. And in particular for PG 7 or 10, I think, to my knowledge, is not known if this is still true or not. There are technical problems. There are a couple of things to be said I want to say here. The first thing is that is important for the talk, as you have seen from the overview, that the Gorenstein property plays a role here. And the first point you see this is that, canonical surfaces are always Gorenstein, and that's one way to say that the volume is integral. But in dimension 3, that's no more true, and I mean, the volume may not be integral, although on this line it will, but we're going to discuss it later better. But it's important to at the end, we'll see non-integral things appear, things with non-integral volume will appear at the end of the talk. And the second thing is that this theorem has an old story, which I don't know completely, but there are, I mean, that the volume is sharp, that the inequality is sharp for arbitrarily high PG is due first to Kobayashi, examples in the 90s. And then there is a long story of papers by Yunkai, Meng, and other collaborators. And in fact, we started this collaboration with Stephen Cochran in 2015, when Meng Chen was giving a talk on one of these older papers where this inequality was proven. I mean, the weaker version of this result we will discuss. That was an inspiring talk for me and in Bayreuth, and then we started working hard with on that. And the point which, of course, you should know, is the first part of the proof, which was already in this previous version of theorems clear, is that the difficult point of the inequality is, to my understanding at least, is to deal with these fibrations in one-two surface. Since the really first 2 pages, I think, of the paper I mentioned deal with this case. So if one way to write the result of these things is that if the volume is smaller than 2 PG minus 6, and see this 2 is definitely bigger than 4/3 here. If the volume is smaller, so it's something, I would say, much bigger, in particular for high PG is much bigger, then your threefold, so a canonical threefold with volume smaller than that, has a map onto P1 whose general fiber is a 1-2 surface. Well, we call it 1-2 surfaces. I was told that in literature there are other people calling them I surfaces. It was explained that this I is because I is the letter after H, so H is Horikawa, so this surface comes after Horikawa. I didn't know that when we started this work. We call them 1-2. Stephen, I think it's a name which explains a bit informative, so a bit more informative, because the volume is 1 and the genus is 2. So since the whole game is about volumes and genus, a 1-2 surface is just a surface with volume 1 and genus 2. And well, the general fiber, so if I assume, okay, I want if I want the surface to be the canonical model of a surface with these volumes, with volume 1 and genus 2, these surfaces are very, very well known, or very well studied already from Kodaira or Horikawa. They are the first famous exception to that Bombieri had to use in this in their theorem, famous theorem on the birationality of the n-canonical maps. So, but the classification of these surfaces is surprisingly easy and well known for decades, considering how important they are, because they are simple divisor in this weighted projective space. You take a projective space with weights 1, 1, 2, 5, which is weights we are going to see a lot during this talk. You take a general hypersurface of degree 10, in fact, any hypersurface of degree 10, which has at worst canonical singularities, is a surface with volume 1 and genus 2, and they are all the canonical models of surface with volume 1 and genus 2. So, when I saw this in the inspiring talk of Machen, I got a little bit thinking about what I knew about the Horikawa surfaces. Because, one of the papers I studied, the first paper I think I studied when I was a PhD student, were this very famous and milestones written by Horikawa in the 70s, which are about modular space of surfaces of general type. So we have already said that the neutral inequality in dimension 2 says that k squared is at least 2pg minus 4. Now the classification of surfaces with k squared equal 2pg minus 4 is in this paper by Horikawa in Annals of Mathematics in 76, which is the first paper of a series of papers. And the subsequent papers are about surfaces with k squared a bit bigger than 2pg minus 4, but the first paper is about 2pg, k squared 2pg minus 4. And so the first part of the paper of Horikawa classified those surfaces. That's the reason why these are referred as Horikawa surfaces. Although, as I was told, as Italian, I have to say, because I was criticized recently not for doing that. This classification was probably, looking at their paper, already known to Max Noether and Federico Enriquez, at least looking at the book. Although, as you know, the paper, things written by Federico Enriquez are not always completely formally okay. And so the first part of the paper of Horikawa was writing down properly this classification. But main point of the work of Horikawa that's important for this talk to specify is that Kodaira was his advisor, and the deformation theory was at the beginning, and so he gave him this paper, these results, the surface to study, with the goal to study deformations, the modular space, because we were really at the beginning of deformation theory at that time. And Horikawa did, of course, a great work, here I have two screenshots of the paper of Horikawa, as I did for the paper of Yunkai, Nang, and Chen Zhang, localizing something which is especially related to the results at the end. So when he studied this classification, I won't cite today in detail. I don't have the time to explain it in detail. But then studying deformation, he said that most of these cases are the generation of other cases. And he found that, in fact, for almost all of them, so if C1 squared is not divisible by 8, C1 squared is even on this line, so it's basically once every 4 cases. But if C1 squared is not divisible by 8, then all these surfaces have one on the same deformation time, and that's the way Horikawa writes it in the introduction. But if you look at the paper and the proof, is really proving much more. It's proving that the modular space is unirational, so irreducible and unirational, not just connected as it's saying here. It's just much more. It's irreducible and unirational. Why there is this fun exception, this special exception, that when the volume is divisible by 8, you get a second deformation type, which means that the model space is disconnected. In fact, it has two connected components, two unirational, irreducible components, but they do not intersect. And these two families are still studied by people because it is not yet proven for all of them is this the surfaces in these two classes are diffeomorphic as real manifold. It's known that they are homeomorphic, but not if they are diffeomorphic as real manifold. Still after almost 50 years now. It's a hard problem, but it's not the problem I'm going to discuss it. So this is just the inspiration for what we did in threefold. So the idea we had is, well, since this is a paper, well, everybody doing surface has read. Well, there are, as in every case, there are exceptions if PG is small, but if PG is big enough, in this case it's at least 7, then the canonical image is a ruled surface, and you can pull back this ruling, and you get a pencil of curves of genus 2. So almost all this surface, I mean, that's have a fibration in curve of genus 2, which is very well known, and is in fact the way I met this surface first in my life, because I did my PhD thesis on fibrations of small genus. That's probably the original idea comes from this. I should mention that in this case, the fibration is always a morphism, which is different from, as you will see, from the threefold case, where, if I go back, this fibration, as you will see, is not defined everywhere. But we are going to see it. But so the way I met it was more than 20 years ago, when I was doing my PhD thesis, because this was about genus 2 fibration. So let me tell you something, I mean, very classic, or you say classical, I mean, very old, on how we study now recently fibration in surface fibrating curves of genus 2. So I take a look at the good. Okay, very good. So let me look at this. So to take a surface, so a genus 2 fibration. So I take a surjective morphism. I have a surface, it can projective, complete, only complex number, however. On a projective curve, I want this to be close, compact. And I ask the general fiber to be a curve of genus 2. So take any fiber. Any fiber. It's important to discuss any fiber. Because the general fiber is a smooth curve of genus 2, but there are singular fiber. And the singular fiber are in fact topologically classified by Ogg, I think in the 670s, I don't remember exactly. And there's 70, 80 different classes. I mean, it's funny, but hugely an untreatable list of cases. But there is this classification, which is purely algebraic, which makes them in 2 classes. And I don't know really who did it first. I read it in the thesis of Margarita Mendes-Lopes, which simply writes, Miles Reid told me at the blackboard once I was in the office. I don't know if that Miles Reid did it first or other people. But that's simple, in fact, and very well known. So if instead of looking at the topology of these fibers, let's look at the canonical ring of this fiber. So we take the same thing. We take the multiple of the canonical system of the fibers, all multiple. This is take H0 of each of them, and you get a ring. And I want to look at this ring. And if the curve is smooth, what you get is, as well known, this guy. So you get X0, 2 generators in degree 1, which are the generators of the G12, the genus 2 curve is hyperelliptic. And then you get an element of degree 3 in 3K, which is called Z, whose zeros are the Weierstrass point, the 6th Weierstrass point of it's in 3G12, so there's exactly the 6th Weierstrass point of the curve, and you divide by a sextant. Well, you can recognize in the case of genus, of course, smooth case, so z squared equals something, you get a double cover of P1 branched at 6 points. But this, in fact, this picture works not only for smooth, but for most of the fibers. I mean, for the general fibers, of course, for smooth fibers, but any fiber which is irreducible or even more generally two connected has this canonical ring. Two connected means that doesn't happen this. So not two connected means that the fiber can be written as a sum of two effective divisors whose intersection is one or less, but less is impossible. So the other, if this is not two connected, means in the case of genus 2 curve means there is this decomposition. So in this case, you can just write two connected as there is not such a decomposition. So they must be reducible, but not just reducible. They must be reducible as a sum of two elliptic curves. They may be irreducible or not. They may be more complicated, but this is in fact. In the general case, two elliptic curves intersecting transversely in a point, named as elliptic tails, and you have more the complicated decomposition, but you always have this, you can arrange this irreducible components in these two subdivisors A and B in this form. And what you get in this form is that, again, you have two generations of degree 1, which are this element of the defining the G12, but then you take, but they are related in degree. There is a quadric. And then you must add one generator in degree 2 to essentially to keep the Hilbert function the same because it is a family, so it must be flat. And then that's it. I mean, you take you keep needing a generator in degree 3, and you keep needing a relation in degree 6, and these are such a things. Such a description includes all possible curves which are not in this form. And this is the composition here, which is allowed to discuss the invariance of genus 2 fibration in a simple way, because what plays a role is just the number of fibers which are two disconnected with a multiplicity, in fact. And this is, I mean, I took it by these papers, which is by me and Fabrizio, which is coming shortly after my PhD thesis. Although I have to say this essentially known to Horikawa, Xiaogang, and I saw it before. The paper is, but that's written in this way, is written there, so for me convenient to cite this paper because I haven't found written in this way there. But I'm not claiming this result for myself. And so the volume of a surface, so now let me assume that the surface canonical for simplicity, but canonical model for simplicity, but it's not really necessary. So the volume of the surface equal, let me jump this, go directly to this expression. You see this 2pg minus 4, which you recognize as the value of the minimum according to Newton inequality. And what you get? Plus 6b. This 6b is, this b is not negative because it's the genus of the base curve b, because the theory, I never assumed b equal p1, if you want, but I will, as you will see now, I will need. And so tau is an effective divisor on b, so this p1 is not, is wrong. This should be b, because this is for every, oh god, there are too many b's here, so sorry, it's the base curve p, it's different from this b, sorry. I hope it's clear. On the base curve, which is supported on the image of the two disconnected fibers. So this is an effective divisor as a degree, and that's marking exactly the special fibers. Of course, as usual in algebraic geometry with some multiplicity, I mean, you expect this to be a reduced divisor, so counting exactly number of two disconnected fibers, but there are situations in which you can degenerate 2 points and you get 1 point, one of these fibers counts twice. So this tau, sorry, I jumped at the part of the discussion. This tau plays a game in this degree of tau. So the volume is 2pg minus 4, sorry, plus 6 times the genus of the base curve, minus a contribution, there is a little odd things, which this negative sign, by the irregularity of the surface, which as we'll see, well, is a little problem for this computation, but we solve it quickly, plus another non-negative number, which is exactly counting the degree of this divisor. So this counting how many the fibers with of the form, two disconnected, of this form with some multiplicity, which I don't want to discuss it, but is quite expectable. We always have it in algebraic geometry. This little odd for my, since I want to discuss the Dirichlet inequality, so the Dirichlet inequality test says that the volume is bigger than 2pg minus 4, so I would like to have just positive numbers, and this little negative number is in fact not there by inequality, a famous of Youngermans and the bar, irregular surface, those with H1 positive, RK squared bigger than more, at least 2pg. So, since I want to study what happens when the inequality is an equality, I can forget about it. I can assume this to be 0. And in fact, what I get is the equality. Now, I wrote k squared because I'm supposed a canonical surface. Equality in neutral inequality is equivalent essentially to be in this equation, genus 2 fibrations, assuming genus 2 fibration, if you want, which for pg equals 7 is not necessary. Equality in the neutral inequality is equivalent to ask regularity and no tau equals 0, which means there are no two disconnected fibers. And this remark allows us to, so this H1 equals 0 is in fact implies that the base curve is a P1, because if the base curve has positive genus, the one form on the curve pulls back to a one form on the surface, which gives you irregularity. So that's, let me apologize for that. The reason why I did a big confusion here on B and P1. So I discussed this for any curve B, but when I want to study things with volume small near the neutral inequality, when the neutral inequality is an equality or not, the equality phase for a little number, I end up with fibrations on P1. And so I essentially reformulated this in this little remark. So this a remark, a definition I essentially invented for this talk. I can say the following. So this what it means is that I can call a simple genus 2 fibration. I say a genus 2 fibration is simple if I don't have any two disconnected fibers. So let me reformulate this definition in a slightly more complicated way. A simple genus 2 fibration is amorphous, X and B, F from X to B. This is between projective varieties of respective dimension 2 and 1, so a surface onto a curve. The curve must be smooth. X may be singular, but at worst canonical singularities, which for surface is ADE singularities, but and I don't really ask the canonical class to be ample, which causes, but a slightly less, which is more natural for one study fibration, so that is relatively ample. I want this to have positive intersection with any curve which is contracted by F. And then I write, I don't want to disconnected fiber. And the way I write, I don't want to disconnected fiber is, well, for all point in the base, let me ask the canonical ring of the fiber to be of this form, which is the form of, which as I discussed, is the form of the two connected fiber. So the quotient of the polynomial ring in 3 variables of weight, with weights 1, 1, 3 biasestic. And then I wrote it as a theorem, but as just a remark, which just put it together very well-known things in the previous slides. We can say that by Horikawa's result, so let's say this is a theorem of Horikawa, or maybe Enriquez knew already, but reformulated in this language, is that if you have a canonical surface with PG bigger than at least 7, there are exceptions for smaller PG, let me insist on it, but if we assume PG bigger or equal to 7, then you have equality in the Noether inequality if and only if X is a regular simple genus 2 fibration, which is a shortcut for there exists a map onto a curve with these properties. So without the strange fiber, the strange fibers. And I want it to be regular, which means H1 of O equals 0, which implies, as I said, that the base must be P1. And this is, I mean, very well-known things, not written in this form probably anywhere I know, but it's very well-known to anybody for 20 years, I guess, more or less. And that was the inspiration of the talk. So this, working on this, we say, well, let us, and then finally I can define, I could do it at the beginning, but I think in this way, you know why did it start for where did we get the idea is important, I think. So what about if we want to study fibrations in 1-2 surface like the work of Yunkai and Menge and other suggested to do? Well, a classification of all the canonical rings of all possible degenerations of family of 1-2 surfaces seems absolutely out of reach. Save time, let me explain it a bit. There are a lot of papers recently by particular Rita Pardini, Sönke Rolenski, Marco Franciosi, Julie Ranna, but also Luca Schaffler and other people studied about the stable, modular space of stable surface of type I. They use usually the other notation, type I. And they have, I think now, studied those, so, you know, the modular space of the smooth things are hypersurface of degree 10. And I mean, the standard modular space is made by hypersurface of degree 10 in P1, P5, like I mentioned before. But what about the special fiber? So to do a theory of fibration in 1-2 surfaces, in copying what I did before, I should know all possible special fiber. Now, even if we restrict to the case of stable fibers, which is what has been studied before, up to now, studying the KSBA, compactification, the modular space of these surfaces, we have, I think, a dozen of different possible canonical presentation of the strengths. Special fiber, we know, I think, already a dozen of different possibilities in this language. And I spoke with the people working on it, and they have no idea. They tend to be very far from a classification. I mean, there should be many other. And so that seems to be very complicated. But what about those the simple ones? That's why we call it simple fibration in 1-2 surfaces. So let's just, I don't understand exactly what the degenerations can be, but let me assume there are not. And there are not from the algebraic point of view, because assuming that all fibers are smooth is essentially, you know, fibration, even for surfaces of fibration with like Bourville, fibrations having general fiber, not as a trivial need to have a singular fibers. But I want them to be algebraically like those the smooth ones. So I suppose a simple fibration in 1-2 surface is a morphism from a trefoil to a curve, which is a smooth projective curve. Don't need to be P1, although it will for the applications we have. But up to now, I'm going to ask the singularities of X to be canonical, at worst canonical singularities. I want to ask I don't need to ask the canonical divisor to be ample, but at least relatively ample, which is the natural definition. And then I ask, that's the key in the definition, that all fibers have canonical ring of the form of the smooth, or the same form as the smooth two surface, which means generated by two elements in degree 1, one element in degree 2, one element in degree 5, and one single relation in degree 10. This is all that we ask. Let me add before one comment. There is a paper by Rolensky and Pardini about this modular space of stable surfaces that says that if you take a stable Gorenstein 1-2 surface, it is an hypersurface of degree 10 in P1 to 5. So we are allowing in all fibrations all Gorenstein stable 1-2 surface. We are also allowing non-Gorenstein, as we will see later, fibers, because this guy can be non-Gorenstein, and we are also allowing unstable thing. But this is supported at the beginning of our work, the idea that this object can be interesting. And now the next slide is the main, maybe the main theorems. So maybe that's a good, if there are questions, if there are no questions, I go on, but I'll give 2 seconds for. Okay, so I go on presenting the main theorem. So this definition, so the paper is published now in 2023 in Forum Mathematics Sigma, where you can see this definition in this form, and took not a lot to find. This is what we wanted to study. Took a bit to get some result on it. And let me start. I want to study from the very last result here. Okay. And this is a theorem which is I'm trying to fix now. I mean the paper now, but we have a proof with starting from the end of the story. But let's say that the chronological order is not the best order to explain math usually. So in this case, the last result is important has to be explained first. I have to explain the importance of the other results. So this is a theorem. I mean, we are going to put the paper on archive, I think, soon with. And I didn't mention that, but everywhere C is, if I don't find the names, C is Kaplan, H is Hugh, P is me, and Z is Zhang. And so this is a collaboration of all the 4 together. The first result of this collaboration is that if we have a canonical threefold with volume equal for third PG minus third, so I'm assuming equality, ignorant inequality. I'm assuming PG bigger than 11, as in, no. Okay, I want it to be canonical threefold. So if you remember, the reason for this PG bigger than 11 comes mostly from the result of Yunkai, Meng, and Zhang, where the assumption was PG smaller than 4 or PG bigger than or equal to 11. Here we have only PG bigger than or equal to 11 because by the classification, there is a classification of those with PG equal 4. I think there is a paper of Yunkai, if I well remember. And there are, if what is going to follow is false for PG equal 4. So one exception is already there. We know a threefold with PG equal 4 and volume for third PG minus third, which is probably 2, which is where this is false. And what is this? Then up to some little more, a little transformation, I can see that X is a simple fibration. Let me read it a little bit backwards. Then X is a simple fibration to surface. So we have this maps, which was already mentioned by the first slide when I mentioned the beginning of the proof of Chen Zhang result. we have a simple X is a simple fibration one to surfaces. It must be regular, which means again H1 of O equals 0 and implies the base curve to be P1, and it must be Gorenstein, which was already known under this. Okay, we use also this paper where it was already known, but on this Gorenstein we are going to speak a lot. So it is not completely true that X has this map, has this morphism, because if PG is bigger than 23, my X can be mapped, in fact, to P1 with a morphism, which is a simple fibration one to surfaces, and X is regular Gorenstein. If PG is a little bit less, from PG bigger than 11, I may need to do a little modification of my X scan, which is in fact a small contraction. So by Klepan, by rational, but the point is that as I mentioned, that the pencil predicted by Chen Zhang is not a morphism. And it's to solve a little bit the point. And okay, and this result in some sense completes what we did before with Stephen, Coughlin, and myself, which is the paper I mentioned before. So if on the opposite we have a simple fibration in one-to surfaces, and we assume Gorenstein and regular, so we essentially are we did it these two assumptions, then automatically the volume is 4 third PG minus third term. This is really a little part of the theorem. I'm going later to explain much more of this, but in this moment, let me just mention this part of the theorem because it explains the importance of the new theorem, because when you put the two theorems together, what you get is that if you want to classify the canonical trefoils with volume for third PG minus third in their modular space, if you want to do the Horikawa's work in dimension 3, at least for PG bigger than 11, possibly also for smaller PG, for sure. As I said, for PG equals 4, you need to do something more, but at least for most PGs, I mean, with some exception, you can classify the canonical trefoils with volume, with equality in the neutral inequality by classifying these simple fibrations. Ness is missing. Which, as we'll see, is much simpler, and in fact is something we did mostly in that paper in 2023 with Stephen Coughlin. So we now, okay. So let me go to the way we. So let me go towards this classification. So if it is clear now that at least for if you believe this theorem, which is put together two theorems, so I'm not going to explain the proof of these two theorems, which are both kind of technical and much different about techniques, I have to say, absolutely completely different. But the applications, I mean, what I want to discuss now is the concrete things. So can we classify simple foundation one to surface? So what these two little bit technical theorems allow to do, which is the probably funniest part, at least for me. And so I have to explain a little bit more about this simple fibration. So that's why the title is about these fibrations. Simple, most of them. In the last slides, you will see something which is not simple. So the point is that it's not difficult to show that if you have a simple fibration you want to surface, then you know that every fibers, if you take the projection of the canonical ring, you can identify the surface with the project of the canonical ring, you get an hypersurface of degree 10 in P1125. So essentially not difficult to see that these P1125s glue together to build a fourfold. A fourfold fibers over the curve, which is a bundle in weighted projective space P1125. So what's a bundle for me is a fibration. So I have a fourfold fiber over B, and all fibers are isomorphic. pairwise isomorphic. They are all P1125s. And inside of this, of each fiber, you find the fibers of a fiber of the fourfold. You get a fiber of your threefolds defined as a hypersurface of degree 10. And so this all together allow to describe the threefold as a divisor is in a fourfold, which is much simpler because the fourfold is a bundle in weighted projective spaces. Now, things I'm planning to do and I'm working, in fact, on it is studying this fourfolds. When I say fibrations in weighted projective spaces are essentially not studied anywhere. So part of the work was doing some part of this work. They are not much different from fibrations in flat projective, standard projective spaces, but there are some differences. And one difference is here. So some of these fourfold are toric. This is a warning. I'm not an expert in toric geometry, but in this case, the toric geometry, I mean, the trivialities of toric geometry are very helpful, but I am not going into deep toric geometry because I don't know, never that did the toric geometry. However, when we move toric geometry, when we try to describe F in toric geometry, we are assuming that the base to be P1, which is as we said, we are interested now in regular things. So in regular threefolds, which are fibered over P1. But it's not true. That's a little, what we're going to see works for this fourfold, but in fact, it's not true that every bundle in weighted projective spaces is toric. But here you see the toric ones. And so let me spend some minutes to explain this description, this toric fourfold, which even if you don't know toric geometry, are very simple. So I start, they are fourfold defined by taking a 6-dimensional, so C to the 6, by a 2-dimensional transaction. So they are very simple since they are essentially like weighted projective spaces, with the difference that you are doing two actions instead of one. So I give names to the coordinates t0, t1, x0, x1, yz. You will recognize that the last four names are exactly those I chose for the weighted projective space P1125. And in fact, the second torus here acts as with weights 0, 0, 1, 1, 2, 5. So lambda times t0, t1, x0, x1, yz is t0, t1, lambda x0, lambda x1, lambda to the square y, lambda to the fifth z. And on the second, for the second action, I'm using weights 1, 1 of t0 and t1, and let me not precise now that the weights of the other four variables, which are going to be specified better in the next slides. At this level, you can take any four integrals, even negative, and what you get is a well-defined fourfold. Well, you have to choose an irrelevant ideal, which is what you have to remove from C6 which tells you what you have to remove from C6 to make the quotient. And with this choice, this T0 and T1, they cannot be, okay, they define a map from onto P1, which is a fibration. I mean, essentially, if you take a fiber, you get you remove these things and you get a standard weighted projective space P1125. So if you are let's say expert of toric geometry, you will see it. Otherwise, just believe me. This choice, whatever A, B, C, D, defines a fourfold which is compacting fibers on P1 by this T0 and T1, and all fibers are 1125s. Now, the theorem of another theorem we proved with Steven is that if we have these two, if we take a simple fibration in 1, 2 surfaces, and we further assume this to be regular, which is, of course, I could like be here, and the regular forces be to be P1, and I ask also Gorenstein, which we're going to discuss it later. Okay, but we are discussing. We should put also Gorestan here. It's not going to be true if I remove this assumption. But if I put it Gorestan here, then this X gets embedded in a bundle. The bundle over P1 in P1, the bundles in P1 1 to 5 or P1 where X is embedded becomes one of the story guys. And not just one of these stories guys. The weights C and D are 0. And the weight A and B, let me forget from now. We will see later this. Let me insist on the fact that the weights of Y and Z are 0. And okay, the element ideal is the same I mentioned before. And the divisor is given by a divisor of by degree 0, 10, where here the order is the order of the rows here. So 0 respect to the first action and 10 respect to the second action. That's essentially the reason why I like to write it this way with these two zeros, because then you can immediately visualize that z squared has by degree 0, 2 times 5, which is 10, and y to the fifth has by degree 0, 2 times 5, which is 10, which means that I can write z squared equal y to the fifth, because otherwise, if it's not bi-homogeneous, you don't get it. It doesn't get any sense. And of course, there may be, we'll have other terms involving the variables x0 and x1, and involving also t0 and t1. And what you can have here depends strongly from the two weights you have chosen here, which up to now you can think still as two integrals a and b. And here reformulated as a function of two other integrals d and d0, because these two other integrals d and d0 have a geometrical meaning I'm going to explain, different from a and b. So if we take these results together with the previous results, you get that if you want to start, we know that all trifles on the neutral line for PG bigger than 23, or even for PG bigger than 11, if we allow this little modification, then are some of this. I call the XD D0, any object of this form, which has at worst canonical singularities. The other assumption of simple fibrillation is automatical. If you assume only at worst canonical singularities, and no, you need to wait, and canonical relatively, no, canonical relatively amply you have, and all the other assumptions are. So the only things you need to get a simple fibrillation, a divisor of this form, to be a simple fibrillation you want to surface, must be with worst canonical singularities. And then it would be a simple fibrillation you want to surface, would be Gorestan, would be regular. It will be also Gorestan. We're going to see it. Yeah, you can see that it's Gorestan essentially because if you look at, there's good things to mention. This F is a singular fourfold because the weighted projective space is with weights P1 to 5 has two singular points, and any bundle in P1 to 5 has a singular points along these 2 points, so it has two sections of singular points, two curves of singular points. One for x0, x1, and z0 and y1, or for x1, x0, x1, and y0, and z equal to 1. But this equation here, lucky enough, missing these two sections, because if you in these 2 points, this part will absolutely always be 0. And well, one of these two will be not 0, and the other one will not. So the equality is not. So this my threefold is going to not intersect the singular locus of the fourfold. So it's a divisor in a smooth ambient. So it is constant. Okay, and so this gives already a classification, but it's not enough. Because I come from modular spaces of surfaces. For me, a classification means I want to see the deformations. I want to see the moduli, and I want to see something more also from this on this DD0. So what are these? Well, that's the reason why I write them, and which numbers are allowed here, because as we see, not all numbers are here. And then what follows is sort of simple to do. I mean, it's the difficult part. Under the carpet is the proof of these theorems I mentioned, but this is not what it comes now as is Algebraic computations, kind of simple. So now we have a lot of trifles, a lot of unidirectional families of trifles. For each value of d0, what I get, let me go back, is a family of divisor. What I get is an open subset of the linear system of the divisor of by degree 0, 10 in a fixed trifle. Fourfold changes when I change d in d0. But x, and then for each of these, I take an unidirectional family, which is an open subset of this, which of course may be empty, because I have to assume that there is an element, that the general element, in fact, has otherwise canonical singularities. And in fact, a direct computation shows that, in fact, you cannot take any dd0, otherwise you can get everything much singular, but the general element in this unidirectional family, to have only canonical singularities, then you need an inequality d0 to be, if you want, the ratio among d0 and d to be included among 1/4 and 3/2. Well, I still haven't explained what are d0 and d, but let's say, now I'm going to do it. But see, we have these two numbers, and we have this relation, because if you make d0 smaller than the 1/4 d or bigger than 3/2 d, then a direct computation shows that the linear system has a base locus where every element has to be two singular, not canonical. Now, the first remark is that this inequality, so at the beginning, d and d0 are not start from being integrals. In the theorem above, d and d0 were just integrals, could be negative. When you arrive to assume canonical singularity, you get this inequality, and this inequality forces 1/4 of d to be smaller than 3/2 of d, so d cannot be negative. And then d0 cannot be negative too. And so here, the minimum among this one reason, if you want, for these two numbers to be good and allow to write nicely the next results, but the reason is that they have a geometrical minimum, which I'm going to explain. The first is coming. So we know that these two numbers must be non-negative, and if the number is 0, it's easy to see that if the minimum is 0, they are both to be 0. And then in this case, the trifle is not interesting, because it's the P1 times a fixed surface. So it's negative dimension. It's not a general type, and of course, it's a simple product. It's the simplest fibration you can think is the product. So this should appear somewhere. It appears here. So let me remove this little case. And so that from now on, the minimum is at least 1. And then you compute the invariance. And the trifles have all the irregularities to be 0, H1 and also H2 to be 0 of O. The genus, for assuming this, is, assuming this minimum to be at least 1, the genus is 3D minus 2. So if I had written this way, it says A and B, then I would have used a combination of A and B to get the genus, but one reason to write this way for me is that I have now one of the two numbers into the game is a deformation invariant, because the genus is a deformation invariant. The two ways are not a deformation invariance, but this combination of them, which is D, is a deformation invariant because it's the genus. It's 3D minus 2 is the genus. So when I go to study moduli, as I want to do soon, I will fix D and move to 0. So PG is 3D minus 2, no irregularities are around, and the volume is 4D minus 6, which is, of course, 4/3 PG minus 32. I hope if I haven't done any typo. What about the canonical system? Because in fact, I'm looking for canonical models, so I would like it to be ample. Well, it's ample if the minimum is at least 3, the minimum, so the game is always about the minimum among the 0. If it is bigger than 3, the canonical system is ample. If it is exactly 2, it's no more ample, but it's big enough. And if it's 1, is also not big enough. And so, in fact, this little difference here is exactly the one who generates this not being a morphism of the fibrilation. Because if this is big enough, I have to get a canonical model, I have to contract something, which is a section. And in fact, the cases where the minimum is 2 are exactly those where I needed in the theorem a little modification for PG among 11 and 22. Because in that case, I have a curve or even to orthogonal to the canonical divisor, and to get the canonical model, I have to do this contraction, this little curve. So this happens only when the minimum is 2. When the minimum is 3, so when the genus is high, then this doesn't appear. When the genus is high, you see that this doesn't appear. It doesn't happen because of this inequality will forces D0 to be rather high enough, rather I2, and then this minimum will be bigger than 3. But for small PG, you get these cases where you have a curve to be contracted if you want to see the canonical model. Good. I have still, I guess, 25 minutes, so as usual, it's okay. So the image of the canonical map, again, okay, I have to explain the geometrical meaning of D0. I want to explain the explain of D0. And let me be quick on this slide so you can write explicitly the canonical rings. And the point is that at least if these numbers are big enough, in this case it's D0 which comes to the game, if D0 is big enough, the canonical image is an Hilbert surface. This was already known, at least for the work of people I mentioned, that if you are in this equation of invariance, the canonical image is a surface and it's an Hilbert surface, and the Hilbert surfaces are classified by a number E, and this number E involves D and both D0. So D0 is, essentially tell me what is the which Hilbert surface exactly I'm into the game, is into the game. In fact, this is only if D0 is bigger than 3, because if D0 is equal to 2, then you see the map goes to an Hilbert surface and then contracts this negative section, so you get a cone of a relation on a curve. And the canonical image becomes even a curve if D0 is equal to 1. So when D0 gets smaller, the map changes a little bit, but there is always an Hilbert surface into the game, and the geometrical meaning of this D0 has to do with the Hilbert surface, but the index is not D0, it's 3D minus 2D0, but it's more convenient to work with D0 for me. And so let me discuss a bit what happens for the singularities of the gen. So what I have now is that I have essentially stratified the modular space. So each, I'm interested to fix the D because I want to study the modular space, and D is a deformation invariance, so it's natural to fix D, but then if you have families where D0 changes in the modular space. And but if you fix D and you move D0 in this range, here I also wrote some equivalent inequality with E, let me ignore them. Of course, you can get families where D0 changes. But if you, so we have some unirational families, because for each D0 you get a unirational family, different dimension, which fill, to give a stratification, decompose your modular space. You want to know how they glue to reconstruct the modular space. And it has an important role to see how the singularities of the general element of this, of each of these strata. Because what it turns out is, let me explain the result. I mean, these are direct computation. There is nothing deep here, nothing complicated. Just you have an equation in toric variety, which is like having an equation in a projective space. Weighted projective spaces, and you look at the fixed locus by Bertini theorem and look at the singularities there. And if the index of the Hilbert surface is small, which in this inequalities correspond to have D0 big, so D is fixed, and D0 at least D up to the maximum, 3/2 of D. The maximum is 3/2 of D correspond to have P1 times P1. as elliptic surface. So then the singular locus is empty, which means that the general element in my unidirectional family is smooth. If I go below D, there's a lot of space up to 1/4 of D, I get some terminal singularities. Actually, it is a double point, which are not exactly ordinary double point. That's the local equation, natural local equation we have. I mean, this variable are essentially the variable we are using. I use the same letters. And the number of this point is maximal when D0 is near to D. So it's 8D0 minus 7D. So if D0 is back near to D, you have a lot of them. As soon as D0 goes down, down, down up to 7, 8 of D, they become smaller and smaller. When D0 is exactly 7, 8 of D, magically you get no singular points anymore. And then again, you get D0 equals 7, 8 of D. So for D0 equals 7, 8 of D, the general X is smooth. Of course, this requires D to be divisible by 8. Or if you want, what is divisible by 8 is something related to PG. Where is it? So it must be PG plus 2 to be divisible by 8. And I guess the volume, if you want to reformulate as in Horikawa, I want to remind to you what I said about Horikawa. You are asking that the volume plus 6 is divisible by 8. And if this happens, then you have a family, a sort of special stratum, at the moment it's just a stratum, where the new smooth threefold shows up. When you cross again this line, and the zero becomes smaller than, say, 7, 8 of D, then you get a curve of singularities. So you get a section of you get a rational curve of singularities, which is a section of my fibration. And this is I think CA1. I mean, it's still canonical, however, but so you still have all these cases existing. And now we can discuss, I think, the moduli. Good, got to run a bit, but maybe not going to. And so we are again at a paper with on formal mathematics, sigma. Now I'm assuming for simplicity, I'm not sure if it's necessary, but just preparing this talk, I realized that I didn't check. This assumption was there because in that time we knew less of what we know now, so maybe it could be a bit weak. It could be stronger than necessary. This assumption, I don't know. However, if at least we assume PG bigger than 7, which is includes those PG bigger than 11, where I know that I'm dealing with all, considering simple fibrations in 1, 2 surfaces, I'm dealing with all threefolds on the neutral line. If we assume D bigger than 3, the threefolds with D0 among D and 3/2 of D belongs all to the same irreducible component of the modular space of canonical threefolds that I call KSB component. KSB, KCH because this contains both the examples of Kobayashi I mentioned at the beginning and those by Yifan Chen and Yonghu, which have been constructed later by generalizing the work of Kobayashi. They are all in this component. So look at this. Let me go back here. So this whole first class is here, first group here. They are in fact only one irreducible. They form just one irreducible component where the general element has maximum D0, which is 3/2 of D or 3/2 of D minus 1, depending on the parity of D, is an open subset, and the other are just specializations of this. But when you go down a bit, if you go in this zone, things changes. And at that time, in the paper 23, we just studied the second case, where we had, which is simple, because the general threefold is smooth. And the first, not so easy, but we could prove at that time just that this this stratum, which appears only when the volume plus 6 is divisible by 8, gives a second component with giving a nice, in my opinion, analogy with the result of Horikawa I mentioned at the beginning of the talk. And so they gave a different irreducible component, of course, only when this is possible, only when d is divisible by 8. No, so the volume plus 6 divisible by 32. Okay. Okay, and okay, this I can skip very quickly. I can prove that in this component, since everything is explicit, I got interested in more in the space. Also, if anybody's interested in the room, I also could prove that the general element in this component is a monitor in space, but the proof doesn't seem to work for the other components, which is an open problem. But I don't have much time left, just 15 minutes if I'm correct, and I still have a certain list of things to say. More interesting, I think. One is, let's go back to the new paper we're writing down, and what we essentially know, let me go back to the scheme here. So if this group of these zeros, when the yields of subsurface are small index, then all these guys glue in a single component. The moral of the next result is that whenever you go down, so you take d0 smaller than d, essentially all the strata create a new component, not just this one, which I already proved, which we had already proved with Stephen, form a second component when it exists. But the point is, all the strata essentially, all the strata should give a new irreducible component. Should, because it's a work in progress and we still have a little hope here. And we can prove it, you know, we would like to have this statement for all remaining d0. So for d0 going from d4 to strictly smaller than d. And up to now, I can do it only for d0 smaller or equal to this number, which is a bit smaller than d. 25th d minus 3 out of 26. And under this, for this d0, we get a new irreducible component. So let me skip the idea of the proof of it. Of course, we can ask it later, but let me go in the last minutes. I have to the consequence of it, and non honest in case I want to say something about it. So what we obtain is the number of irreducible components of the modular space of canonical trifles with PG bigger than 11 and 4 cube is 4 third PG minus 2 third is essentially the integral part round down of PG plus 6 over 4, because this PG, if I could extend this theorem before to also to this d0, where I don't really know if they are irreducible, the strata form irreducible components, or go to a specialization of this KCH component. And in that case, if they were also irreducible component, as I in fact imagine, then the number of component would be exactly this number, which is nicer. Otherwise, could be a little bit less. But still, we have a lot of components, and we essentially know all of them. This little stratum, I cannot. So, the few strata, I cannot really understand where they go. I think there should be components, irreducible components as well. And this is nice that the way there is when we were working, there is a paper by Julie Renat and Sonke Rolensky studying the stable Horikawa surface, so the stable compactification of the surface with k squared equal to PG minus 4, and they also get a lot of components. And the description is much similar to our description. In fact, it's part of the work is inspired by the paper by me and Stephen. Here I had a slide where the minimum, when the minimum is 1, where we find things which are, you know, when the minimum is 1, the canonical system is no more big enough, but we can still investigate the canonical models. There are a few cases. And we got 3 examples of trifold with small volume. 2 were already in literature in this paper by Meng Chen, Chen Zhang, and Li. And the third one, I think, I couldn't find it anywhere. Let me spend the last 10 minutes in the non-Gorenstein case, because that's the things I'm more interested in now. Because I spoke all the time about simple fibrillation that are Gorenstein. Because we have this theorem at the beginning that if you want equality in the neutral inequality, we need to assume Gorenstein. But in fact, if we have equality, if and only if it is Gorenstein. But there are simple fibrillation which are not Gorenstein. And to get a simple, in fact, a simple fibrillation in 1-2 surfaces is automatically 2 Gorenstein. The assumption we gave is implies, that's proved. That's simple. Automatically 2 Gorenstein. And these are the examples. You take the same toric fourfold I introduced before, but I changed the way. Here I change respect to the fourfold I discussed it in the Gorenstein case. I changed just these 2 weights, and these 2 weights makes so n is an integer that z squared and y to the 5th are now different degrees. So z squared has degree minus 10n 10, y to the 5th has degree oh gosh, minus 10n 4n, and so minus 4n 10 for z squared, minus 5n 10 for y to the 5th. Sorry, I'm tired probably, but if I multiply, so to get something homogeneous, I have to multiply y to the 5th with a polynomial in T0 of degree capital N. And so what happens now, if you take such an equation, is that your divisor is no more contained in the smooth locus of the fourfold. Because if you take x0, x1, z equals 0 and y equal 1, and value is 0 to 1, here you get one of these 2 sections of singular points in my fourfold. And my threefold intersected exactly at the zeros of this polynomial. And so you get with multiplicity n singular point of the threefold, which turn out to be 2 Gorenstein, non-Gorenstein singular point. So such a picture here as volume 4/3 PG minus 10/3 plus something, which is exactly 1/6 of this number n. And let me insist on the fact that this is a half integral, which may not look clear from this denominators, because we are dealing with something which is 2 Gorenstein. And so now I can reformulate the theorem by me and Stephen, which I formulated in a weaker version before. If I have a simple fibrillation in 1-2 surfaces, so I get this definition I explained, relatively ample, every fiber is an hypersurface of degree 10 in P11 to 5, then my threefold is always 2 Gorenstein. Is Gorenstein if and only if has equality in neutral inequality appears, because a simple fibrillation in 1-2 surface, if regular, which in fact is a simplification here, we can state something similar in the non-regular case, but the regular means gives here P1, but the formula changes. But if I assume regular, then I get the volume 4/3 PG minus 10/3 plus 1/6 of the number of non-Gorenstein point counted as usual, possibly with some multiplicity. And the Gorenstein case is exactly the case when these numbers are not there, so when n equals 0. Okay, in fact, n is better defined as the intersection number. It's the intersection number of my threefold with this curve, curve of singular points I defined. Now, when we had this theorem shortly before that we put our theorem in archive in 2022, Hugh and Zanger came out with this blueprint on archive. That's the starting point of the collaboration that I gave you already the main result. Actually, some of the results, but also these last results on the deformations are in the collaboration. They could prove that if X is a minimal, or minimal is a bit weaker than canonical, but that's not an important difference. Threefold with PG bigger than 11 and they assume the volume to be smaller than, I mean, they vote in a slightly different way. I make it shorter for this talk. 4/3 PG minus 10/3 plus 1/3, so plus 2/6. Let me write it as 2/6 because here for me it's important to count how many sixths, how the difference with the volume. Then they prove that if you have a minimal threefold with this PG bigger than 11 and volume is small enough, then it's automatically 2 Gorenstein. And the volume cannot be anything, but it must be 4/3 PG minus 10/3, or 4/3 PG minus 10/3 plus 1/6, or 4/3 PG minus 10/3 plus 2/6, which is exactly the numbers we have. They are really independent by papers coming with completely different strategies. And they also prove that X is Gorenstein if and only if this number is 0. The second and third meter line, how they call it, are made by 2 Gorenstein things that are not Gorenstein. And so we have a lot of simple foundation we want to serve also on these lines, and we don't know any examples, at least for PG equal 11, on these lines, for PG at least 11, on these lines that are not simple federation in 1-2 surface, but we have a lot of them. And so my question is it true that what is the maximum number, if, or no, can be a maximum, can be a sup, such that if PG is bigger than something, I don't know if it's 11 or 7 or 235, the right PG, but there is some, such that all threefolds with volume smaller than 4/3 PG minus 3/3 plus this something are regular simple federation in 1-2 surface of P1. What if this is question started essentially the collaboration with Yu and Zhang, and what we did in this language says that if I put a 1/6 here, this is true. If the volume is smaller, strictly smaller than 4/3 PG minus 10/3 plus 1/6, by, let me go back, this theorem, PG bigger than 11, by this theorem, you get a 0 here. So it must be 4/3 PG minus 10/3, and then we have that theorem again in the new paper with Yu and Zhang, claiming that you get equality, and then it's a simple federation in 1-2 surface. And finally, so it could be 1/6 and 2/6. The second and third meter line may be, at least for PG bigger than 11, made only by things we can write in this way. That's let's say future projects essentially. And what I'm going to write here is the next examples, which are in fact will be found thanks to an email by Yongkai, and I think are the best we can do. Which are those? Which shows that if I put the 2/3, which is really 4/6, I should write 4/6. There is something different. There is something which is not simple. Well, the point here, let me get 2 minutes. So the point here, essentially, you get the same, very similar picture to before, but I'm adding one variable in degree 3. And I'm putting weights, so it's this minus 1 here is to make a T0 here. So this equation, so I get 2 equations now. I get 1 variable more in degree 3, and 1 equation in relative degree 3, which for T0 equals 0 eliminates U, and you get a standard 1-2 surface as before. But on this, for T0 equals 0, you get a special, you get really a stable surface. We took this from the list of 2 Gorenstein stable 1-2 surface found by Rolensky, Pardini, Franciosi, and Dalla. And this guy now is no more 2 Gorenstein because it has a little singular point where this T0 vanishes, which is of Gorenstein index, factoriality index 3, Gorenstein index 3. So you get a threefold, which has volume PG is something, so growing with this A. And the volume is in fact not enough integer because this guy is 3 Gorenstein, not Gorenstein, And so there's not Ugonstein, and so this guy, this variety has no simple federation in 1-2 surface, because if it had another map, even another map, which would be a simple federation in 1-2 surface, would be 3 Ugonstein. It would be 2 Ugonstein. This is not. And so, summing up and my concluding, we have Ugonstein regular simple federation when they have volume 4/3 PG plus 4/3 plus 1/3. And for PG, at least for PG bigger than 11, they give all canonical trifoots with these invariants and allow us to write, to completely understand with this little gap, sorry, up to now for the modular space. The non-Gorenstein regular simple federation may do something similar on the for bigger volume, so for volume 4/3 PG plus 1/3 plus n6th and bigger than 1, we get the non-Gorenstein regular simple federations that are 2 Gorenstein, not Gorenstein. And we are working on this understanding if this we can extend this results also to this, at least to this, the case n equal 1 to start with. But if we go to 4/6, then we have example with PG Algebraic that has, of course, still federations in 1-2 surface, but not simple, and so the picture becomes more complicated, as you can expect. And so the last slide is a picture where I show you what I do understand, a sort of geographical picture. Blue dots locate Gorenstein simple. Well, I can show it is better. So on the x-axis, I put the James. On the y-axis, I put the volume. And this blue line is given by Orikawa. Neutral inequality tells you that at least for PG bigger than 11, which I'm doing, there is no, everything is over this blue line. And you see, we have classified the blue line. These are spots here for which invariant you get our modular spaces. On the green line, on green lines, we have all simple, so the simple federations that which are not Gorenstein construct things on the green spots. And possibly I wrote the first and the second neutral line according to Wezanger, those first two, and can go on, of course. And at which half integer, you see these are half integers. Now volume, you can, on these lines you can get simple federation in 1-2 surfaces that we don't know at the moment if they are all possible trifold or not. If you go to the red line, which is the 5th, so when you have the 4/6, then you can see that you still have green dots, simple federation in 1-2 surfaces, where the volume is half integer, in fact integer, because n is even. But the red lines, the red spots, so you see that the volume is not integer, and there are other examples we have. And that's all I understand that we have to now. So I think I will stop here and thank you for your attention.
Thank you.
Yeah.
So thank you very much for the nice talk. So any questions?
So if you take so case B and the generation of 1-2 surface, is it always contained in P1125?
Say it again. Sorry, you want to know if the
So
definitely.
if you take case B a degeneration of 1-2 surface, all are contained as a hypersurface in 1125.
So Gorenstein stable degeneration of 1-2 surfaces are contained in P0125 as an hypersurface of degree 10. This is proved by Franciosi, Pardini. If you remove stable, I don't know. If you remove Gorenstein, no. In fact, this example here is the first, sorry. Here you see, if you take the fibers here for T0 equals 0, what you get is a complete intersection and the P11235 over cubic and an upper surface of degree, and an upper surface of degree 3 and one of degree 10. But this cannot be written as a hypersurface of degree 10 in P125. You cannot remove this tree here. And well, if you look at the classification of Pardee, I don't remember now all cases they know, but there are other degenerations which can be written as complete intersection in higher dimensional weighted projective spaces. And I think also there are degeneration with can't be written this way. Schaffler and other people have done degeneration which are not even, I think they are not even Kugo-Einstein, which is probably not interesting for me. But so the good, so no. For the Gorenstein stable case, yes, this is true.
So here you showed an example that the 3-fold has 3 Gorenstein singularities. So is it possible to construct similar example with higher index, for example, like index 5 or index 7?
So that's again a good question. Yeah, the answer is yes. We did it. I don't remember now. The point is, but is sort of simple in the sense that. When they do the Kugo-Einstein, the classification of some, they study some Kugo-Einstein modulus, the stable. So what the inspiration here from the modulus, what we know about the modulus space of stable 1-2 surfaces. And I have a couple of slides of the talk of Rolensky, and came in Trento last month, in fact. And they have 2 Gorenstein examples. But the two Gorenstein examples are again hypersurface of degree 10 in power 1 to 5, and you have in fact seen them in this examples here. So that's when you get something like this. You get some singular point, you make it pass through your equation of degree 10 passing through the points, singular point of index 2. Then they have this 3 Gorenstein case, which is the one I use it to classify this. To do this construction, and they have 2 or 3 other Kugo-Einstein examples, which I don't remember by heart, which have different index. And if you use them, I tried it, I did it, but I don't remember now the result. But the point is that I raised more here, so more than 2/3. But that's you can do. I mean, I can do it. I mean, you can do it. I can do it. Everybody can do it. Just do the same game, taking the equation they have, because of course, if you add a random variable with, a variable with a random weight, you get things very singular. But all these examples, all these elements in the model, in the boundary of the stable modular space, can be put in such a fibration, and they add each of them as a sort of how do you call it, Horikawa index, like for fibrations. Add something to the bottom, and those that I know add more, and you can do them, and you get a sample which I think 5 Gorenstein is in the. I mean, there is you need a fiber which is 5 Gorenstein. You put it there, you get a trifold which is 5 Gorenstein, and 5 and I think is there. I don't remember now which prime number they have.
Okay. Yeah. Thank you. Any other questions? So in many of your statements that you assume the genus greater or equal than 11. So genus greater or equal than 11, this is kind of the technical condition that we need in our work. So, but I'm wondering that in your setting, is this really essential?
That's a good question. For most of our results, what we really need, I think, can be reformulated by if I know that the canonical image is dimension 2. Although I can replace PG bigger than 11 by canonical image of dimension 2.
Yes.
In most of them. But if I do understand properly your result, but this should be, you should explain it to me. The main problem in the gap is the possibility of having things with canonical image of dimension 1, right? So if you can, so if you can remove them, then I can probably lift my results. Most of them, but for PG equal 4, you know, this double core, I think it's a, you know better than me. It should be is a double core for P3, right? There is a
I think
triple with PG equal 4 and volume 2, which now I don't remember. It should be very simple, which doesn't have such a federation. So,
I think in the case PG equal to 4, either double cover over P3 or maybe double cover over certain P1 bundle over F2 or F0, something like this.
So at least I will need PG. I to put PG bigger than 7. I mean, I had to put, you know, if I was result PG bigger than 7 to remove the cases where such a fibrillation, the genus 2 fibrillation does not exist. And maybe here it could be true for PG bigger than or equal to 5. And if you could prove, naturally I cannot, but if you could prove, close this little gap in your theorem and prove close this gap and prove neutral inequality, maybe using this I can probably I would say probably I could see if our theorem lifts to PG bigger than 5 or there are other exceptions, which I don't really know.
Okay. And also in your construction that you are kind of considering the one to vibrations. So I'm wondering that if we want to study, for example, the 4-fold genotype, then what kind of simple vibration that in your mind? If we want to consider 4-fold genotypes, so maybe we want to consider some kind of vibration over P1. So what type of 3-fold in your mind should be the right candidate to start with?
I don't even, I have to ask to, I think change and I don't know him, but I was already asking this question, and people told me the right. Mice told me what are the right object to study. I forgot it. I mean, I have it written somewhere. That's something I have to do with your indication. So yes, there are some results about you know, the starting point is which foundation your questions, and Mice told me really for 5-folds what should be the 4-fold to consider, and I wrote it somewhere, but I didn't tell me why. So I have to look in the references to because you know it took a lot of me to and you know I spent the most of my life on surfaces. So already working on 3-fold has been an effort, and now I'm gonna say something. And then I would like to go on like we want, but I have some literature to study and any indication on because there are some paper around studying the higher dimensional things, and I don't remember now, but I should do some better research on it to see, because I think I would expect something similar to happen. I wouldn't say on any dimension, but at least if you, I mean, maybe at the point you need to consider vibrations on things which are not a completely, they're not a hypersurface. That could make a problem. If the fibers involved in a similar neutral inequality are hypersurface in a weighted projective space, then I would expect something similar to be possible. But they have to study. They have to study more.
Okay, any more questions? Okay, so if not, let's thank Roberto again. Yeah, thank you very much.
Thank you for all of you. Thank you very much for the invitation, and thank you all of you for being here and for nice questions as well. Thank you.
Yeah.